Measures of variation provide information about how dispersed or spread out our data set is. So for measures of variation, we will discuss the range, the interquartile range, and then we will look at a graphic display in the form of a box plot that will show both. And from there, we will move on to the concepts of variance and standard deviation. We'll start with the range. The range, simply stated, is the highest data value minus the lowest data value. So in our data set, our highest value is 90 and our lowest score is 22. So we have a range of 68 in our data set. Now, we are next going to turn to the interquartile range. The interquartile range gives us the range of the middle 50% of the data. So in order to get to that, we have to subtract quartile 1 from quartile 3. So if we take Q3 minus Q1, we will then have the interquartile range. Let's take a look at it on our graph. Quartile 3, 78. Our quartile 1 is 67. So when we do the subtraction, we get 11. So our interquartile range then of this data set is 11. Now we're going to take all of these numbers and put it into a graphic display called a box plot. Again, we have the highest value of 90, quartile 3, 78, quartile 2, 72, quartile 1, 67, and our lowest value, 22. So let's talk about the parts of a box plot. Here we see an enlarged version of it and where the positioning is. Sometimes it's called a box and whiskers plot. Why? Because of those lines that go out, and then the dotted lines kind of become the whiskers. So sometimes you'll hear the box plot referred to as a box and whiskers display. Now, you'll see that the box very clearly shows that Q3 in the top of the box, Q2 in the center, there's a skinny line there, which is the median, Q2, and then Q1. And then we have the dotted lines taking us up to the highest value and to the lowest value. So that is essentially what a box plot is going to show, and it's going to show those five numbers. Now, another function of the box plot, though, is to show if there are any outliers in the data set. So we use the measurement of the interquartile range to determine whether or not a particular value that seems really high or really low is an outlier or not. So what we will do then is calculate, we calculate 1.5 times the interquartile range. If we multiply 1.5 times the interquartile range, what the product of that, if we take that number and add it to quartile 3, above quartile 3, and we subtract it from quartile 1, we will have these boundaries, and these boundaries are called, referred to as fences. Now the fences mean that any value that is above the upper fence is considered an outlier, and any value found below the lower fence is also an outlier in the other direction. So let's take a look and see if, in fact, we have if we even have an outlier in our data set. So we have our 4 values. We know that we're taking a look at the interquartile range times 1.5, which is 16.5. So if we add 16.5 to 78, which is quartile 3, we will get 94.5. And all of our values fall within that range. There is no value that goes above that. So there is no outlier above the upper fence. Now let's take a look at the other lower fence. We have the interquartile, quartile 1 times 1.5 times the interquartile range, which is 67 minus 16.5. Now there, we will get, that is our lower fence, if we multiply that. But our lower fence then is 56.5, and look at what our lowest value is. It's 22. So that indicates that we have a value that lies below the lower fence, or the boundary where we would determine if something is an outlier or not. So let's take a look at this a little bit more in depth. So we have our upper fence and our lower fence. No problems with the upper fence as far as outliers are concerned, but when you take a look at the lower fence and the value of 22, it falls below what we would call the boundary, or the lower fence. Now, what do we do with that, and how will that impact the way the box plot will look? Well, it will change it a bit. What will happen in this situation is that we still have quartile 3, quartile 2, quartile 1. And in this case, since we have no outliers going in the higher direction, the whisker just goes to the regular highest value that we did before. However, here, because we have an outlier below the fence, the whisker then will extend out to the lowest value that isn't an outlier. So in this case, the lowest value that isn't an outlier is 64, and you can see that in our line of numbers. And then that the 22 is clearly an outlier, and that is represented by some kind of a dot or some kind of a recognizable symbol that indicates that it lies outside of the range of the box plot. So that is a case of an outlier, and we had an outlier in this data set. Now we are going to move on to calculating what is called the variance and the standard deviation. The variance, let me give you a mathematical definition of variance. The variance is the sum of the squared deviations from the mean divided by the count minus 1. And the standard deviation is the square root of the variance. Now, perhaps you understood that explanation totally clearly, but perhaps not. For most people, that particular definition wouldn't be crystal clear at the start. So the best thing to do in this situation, actually, this is one of those cases where going through the steps is actually easier than starting with a formula. So we want to ultimately know, and this is where we're starting with the variance, we want to know on average how far each data value is from the mean. What is the average distance? So, and these distances of these individual data values from the mean are called deviations. So let's continue working with our pretest scores and see how that is. So now you'll see on the column on the left each of the individual values. We're taking each value and subtracting the mean from it, and then we get what are called the deviations. So if we go line by line by line by line by line, remember what we're trying to do is finding the average deviation, right? So if we go through each of those individual subtractions, what will happen? Well, if you go through them, if you take the time to actually write them out, what's going to happen is that you're going to get a big 0, which can be very frustrating. It's a 0. So how does that help us? It doesn't help us at all. But it's interesting because the question is, well, why did that happen? And it's because that the positive and the negative numbers canceled each other out, because remember, we're referring everything to the mean. So when we add those numbers all together, we get a 0. So what do we do? Well, what we can do is take each of those deviations and square them. If you square those deviations, now we have positive numbers that we can actually utilize and do something with. So we can then take each of those deviations that we had. They're not wasted, except that we have to use them in order to square them so that we have numbers that we can work with. So if we do that, we start with 400, 196, 100, 36, 16, 4, 4, 4, 4, etc. Then we will get the number 864. Now, what we will also do then is we'll take 864 divided by 11. Because remember, we are dividing by n minus 1. So if we take 864 divided by 11, we will get 78.5454, whatever, it goes on and on. But essentially, it's 78.54. So now we have an entity that we can work with. But before I go any further, again, you might be asking the question, why do we subtract n minus 1? Where did that come from? Well, it's not germane to my explanation of what we're doing right now. So what I can say is that Dr. Fossey talked about why n minus 1 in his lecture. So go back and refer to that if you want clarification on why we use n minus 1 versus just a plain n. Okay, so we take the total divided by 11, and we get 78.54. This number is called the variance, and we were able to divide it out. And here is the formula for the variance. Maybe by looking at it now, the different pieces of it may fall together, because again, we're subtracting the mean from each of the individual data values, squaring them, and then dividing by n minus 1. So in fact, that's what we did just now, but that is the formula indicating the steps that we just conducted. So we have a number now. Great, right? So we're done. Are we done? Well, not quite. Why are we not yet done? Because when in the process of squaring those deviations and adding them up and taking the average of that, remember, we had to square everything in order to get to those numbers that we can work with. So everything is squared. So what do we do to unsquare that which we squared? And what we would have to do then is to take the square root. So if we take the square root of 78.5.54, or just 78.54, and we round it to 2 decimal places, we will get an 8.86. Okay, now that's a number that we can deal with. We can say that the average difference from the mean of the values in this data set is 8.86. And there's the formula for the standard deviation. You'll note that it's basically the same formula that we had for the variance, except this time we have a square root. So we're taking the square root of the variance to get the standard deviation. It's always important, though, when you have a value to state it within the context of what we're talking about. The other definition was accurate and fine, but wait, what are we talking about here? We're talking about scores on this pretest. So stated in context, we can say that the average difference from the mean of 70 of the pretest scores for Statistics is Sexy 101 is 8.86. So when you look at it from that way, the score, we have a mean of 70 and a standard deviation of 8.86. So that gives us a pretty good idea of how the students are doing. Now keep in mind, this is not the final exam, this is a pretest. So I would say that that score, those scores and that standard deviation is not bad at all for a pretest. The instructor should be happy. So this wraps up our introduction to numerical data. See you next time.